everyone, and welcome to This Explainer. Today, we're setting off on a really incredible journey. We're going to travel from the macro world, the stuff we interact with every single day, right down to the microscopic atomic level to uncover the actual brains of our devices. It's basically a story of how simple, everyday sand is completely transformed into the supercomputers that run our modern lives. Okay, let's dive into this. Just think about your smartphone for a quick second. How exactly do we fit literally billions of individual electronic components onto a chip that's smaller than your fingernail? I mean, it sounds like pure science fiction, doesn't it? Well, the answer lies in a genuinely miraculous technology called VLSI, or Very Large Scale Integration. 50 billion. Let that sink in. To truly grasp the magic of VLSI, we really have to understand the sheer scale we're dealing with here. A modern high-end processor doesn't just have a few thousand or even a few million parts. It contains upwards of 50 billion transistors, and they're all meticulously arranged in an area you could literally cover with a thumbprint. It's an engineering feat that absolutely borders on the impossible. And the absolute most crucial point here is that without very large-scale integration, the modern world as we know it just stops. Every single time you stream a movie on your phone, every time an AI generates an image, when a modern car's anti-lock brakes engage, or say when a satellite beams GPS data back to Earth, you are relying on VLSI. It's this invisible engine powering aerospace, life-saving medical devices, and the entire Internet of Things. Section 1. A history of shrinking tech. Let's look at a quick timeline. So, it all actually started back in 1947 at Bell Labs. That's when the transistor was invented, which thankfully replaced those massive, super fragile heat-generating vacuum tubes. Fast forward a bit to 1958, and innovators like Jack Kilby and Robert Noyce figured out how to put multiple components onto a single piece of material, giving us the integrated circuit. By 1971, Intel released the 4004, the very first commercial microprocessor. And today, we're manufacturing hyper-advanced AI accelerators that can literally perform trillions of operations every single second. Now, the guiding principle behind this relentless, non-stop march forward is famously known as Moore's Law. Back in 1965, Gordon Moore made a pretty brilliant observation. He noticed that the number of transistors we can squeeze onto a chip doubles roughly every 2 years, all while the cost per transistor actually drops. Now remember, this isn't some fundamental law of physics. It's more like a self-fulfilling prophecy of engineering that constantly pushed the whole industry to make devices smaller, exponentially faster, and incredibly cheaper. We started out with SSI, or small-scale integration, which literally meant fitting maybe 1 to 10 logic gates on a single chip. From there, we moved to medium and large-scale, hitting the thousands of transistors mark. That eventually ushered in the VLSI era with millions. Today, though, we technically live in the ULSI era, ultra-large-scale integration. That's where we're packing those tens of billions of transistors into just one single processor. Which brings us to Section 2, the science of silicon. Let's look at the actual building blocks. Let's take a quick step back to basic high school physics. On one hand, you've got conductors, right? Things like copper and silver where electricity just flows freely and easily. On the other hand, you have insulators, like rubber, plastic, or glass, which block electricity entirely. But to build a computer, we can't just have electricity flowing or stopping all the time. We really need to control it. We need a middle ground. Enter the semiconductor. And the undisputed king of semiconductors is, of course, silicon. But why silicon? Well, for starters, it's incredibly abundant. I mean, it's practically just refined sand, which keeps manufacturing costs incredibly low. Plus, it's chemically stable, it has amazing electrical properties, and here's a massive bonus. It naturally forms a really high-quality insulating layer called silicon dioxide. And that layer is absolutely vital for building microscopic circuits. But here's the catch. Pure silicone isn't actually all that useful on its own. To make it work for us, we use a really clever process called doping. This is where we intentionally introduce tiny amounts of impurities into the silicon. If we add elements like phosphorus, we get N-type material, which gives us extra negative electrons. But if we add something like boron, we get P-type material, and that actually creates missing electrons, which we call holes. Now, when you take that P-type material and that N-type material and you join them right together, you create what's called a PN junction. And this right here, this is the fundamental foundation of all modern electronics. The behavior of electricity as it moves across this junction is the literal basis for every diode, every LED, and every single one of those 50 billion transistors sitting inside your smartphone right now. Section 3.
how CMOS powers everything. Let's talk about the dominant architecture. So CMOS, it stands for complementary metal oxide semiconductor, and it's the dominant architecture of modern digital electronics. The absolute magic word here is complementary. CMOS brilliantly uses two different types of transistors, NMOS and PMOS, working together in tandem. They're essentially a perfectly matched pair, balancing each other out to execute digital logic flawlessly.
The logic flow here is incredibly simple, yet totally elegant. The most basic building block in CMOS is an inverter. When the input is a 0, the PMOS transistor turns on and the NMOS turns off, giving you an output of 1. Flip that input to a 1 and the exact reverse happens. PMOS turns off, NMOS turns on, and you get a 0. Because one transistor is literally always off, there is almost zero static power leaking through. This brilliant little dance is the exact reason why your phone's battery can actually last all day instead of just melting right in your pocket.
When you combine all these factors, the advantages of CMOS are pretty undeniable. You get incredibly low power consumption, blistering high speeds, excellent immunity to electrical noise, and you can pack these transistors together incredibly densely. This perfect balance of sheer efficiency and scale makes CMOS the absolute go-to architecture for CPUs, graphics cards, and pretty much every integrated circuit manufactured today.
Section 4. Designing the microworld. Let's look at the VLSI design flow.
You see, building a modern VLSI chip is honestly one of the most complex, highly structured efforts in human history. It flows through 5 macro phases. First up, you need the specification and architecture. Like, what exactly is this chip going to do? Second is RTL design and verification, which is where engineers write code to design the logic and then rigorously test it. Third is synthesis and physical design. That's translating all that code into an actual geometric blueprint made of billions of microscopic wires and gates. Fourth is fabrication in multi-billion-dollar foundries. And finally, rigorous testing before it ever reaches your device. Because this entire process is just so monumental, the career opportunities are incredibly diverse. Whether your passion is writing a logic as an RTL designer, ensuring absolute quality in design for tests and static timing analysis, exploring FPGA hardware, or even solving the ultimate 3D puzzle in physical design, the VLSI field is constantly looking for bright minds who are inspired to build the future of our technology. Finally, Section 5, Beyond Moore's Law, Pushing the Limits. The reality is, shrinking transistors isn't as easy as it used to be. As we push components down to sizes measured in just a few atoms, we're facing some truly immense scaling challenges. The chips generate massive amounts of heat, power leaks where it really shouldn't. The manufacturing complexity is just staggering at this point. And crazy enough, at these tiny dimensions, actual quantum effects start interfering. We're talking about electrons literally teleporting across physical barriers where they aren't supposed to be. But, engineers, they're never deterred. The future of VLSI isn't just about making things smaller anymore, it's about making them smarter. We're currently moving toward chiplets, where we break big chips down into smaller, modular pieces. We're building 3D integrated circuits, literally stacking transistors on top of each other like microscopic skyscrapers. And on the absolute bleeding edge, we're exploring photonic computing that uses light instead of electricity, and even quantum computing to solve problems that classical chips could never, ever touch. We've gone from bulky, glowing vacuum tubes to 50 billion transistors right in our pockets in less than a century. But human ambition is pretty much limitless. So here's the question. When billions of transistors are no longer enough to satisfy our hunger for computing power, what impossible technology will we build next? Take a second to marvel at the magic sitting in your hands today, and definitely stay curious about what tomorrow will bring. Thanks so much for joining me on this explainer. I'll catch you next time.